Hey, welcome back to AP Physics 1. It's been a while, but I'm back. So for this lab, we're going to be testing the conservation of momentum. We're going to be looking at an inelastic collision. So one of these objects will be stationary, the other object will be moving, and then afterwards they'll be moving together. The goal for this lab is to determine what the mass of this second object is. The second object is going to be at rest. The first object is going to move right through the photo gate. Once it moves through there, it's going to have initial velocity. They're going to stick together and hopefully move through the other side like that. This is on an air track, so that reduces the amount of friction that could be possible, and therefore we eliminate any external forces. So momentum should be conserved here. Now, a few things that we want to take into consideration before we do this lab is what are the masses? The mass of this object right here, this is the first object, the one that's going to be moving in the beginning, is 0.186. 0.186 is the mass of this object right here. The mass of the stationary object is going to be, well, that's what you're determining. I'll tell you at the end of the lab what the actual mass is, and then you can do a percent error of it. Okay? The other thing you want to know is what the length of this flag is, because we're going to be using gate mode. So as soon as the flag goes through here, we're going to read a time. You take the length of this flag, which is 4 centimeters, convert that into meters. You're going to take that length and divide it by the time I give you here. There's going to be another time right here. I have to take the difference of it, so I won't be announcing that as I'm recording, but I'll put it up here each time I get the value, okay? So, what are you trying to do once you've got velocity here and essentially velocity here? You're going to be plotting a final velocity versus initial velocity graph. Do some sort of manipulation using conservation of momentum, and you should be able to determine theoretically what the mass of this object is. I guess it's experimentally, and then you're going to verify it with like the actual result. All right, so this is, come on, get to rest. There might be bloopers here, but a little bit of errors didn't hurt anybody. So let's see. As you can see, there's already an error. This thing is moving in this direction here. So we need to raise this elevation a little bit. A little more. I said raise. I go. Raise. All right, let's now. Still. Woo. No, almost. There we go. There we go. Right there. So let's begin. Remember, the length of this is 4 centimeters. So convert that into meters. I'm going to start reading off the times on the gate mode. All right. So I'm going to be, launching it at different velocities. And so different velocities will result in different final velocities at the end. So for the first one, we'll edit that out. Okay, so for the first one, there we go. The time through this gate is 0.065. 0.065. And the time for the second to find the final speed here is going to be written right here somewhere. So I'll edit this and I'll put up the time for that value. All right, let's repeat. All right, let me put this through here, keep it stationary. I'm gonna use a different speed. Okay, so the time through the first gate was 0.0527, and the time through the second was up here. All right, we'll do two more. actually move this over here so I might do it a little bit quicker. Reset. So ready? That's too close to the first one. Let me choose at a different speed. Still kind of close to the first one, but we'll take it. So the time through the first gate is 0.0605, and the time through the second is this value right here. All right, two more. Try to do a slow one. Next one. That didn't work. Let's try that again. That didn't work. Let's try it again. It's giving me the same times. Okay, so the time through the first gate is 0.0493, and the time through the second gate will be up here, and that'll be whatever that value is. One more data point, and I think that should be good. That looks better. So the time is 0.0469, and the time through the second was 0.2373. So you will plot a final velocity versus initial velocity graph, and then the slope of that will help you determine what the mass is. Remember, in order to get this equation, you have to use conservation of momentum. So the momentum before is equal to the momentum after, and then you can write an equation in the form of a line to solve for M1, M2. And that's it for this part of the lab. The second thing I want to do is just look at one example of this, where I'm going to take the weight off. They're almost the same weight. It's not going to be identical. And what I'm going to do is I'm going to flip the magnet side, so now they're going to reflect each other, okay? And what I want you to do is to tell me, based off of what the information here I'm going to give you is this collision going to be an elastic collision or an inelastic collision? So take the values that you get here, write out some equations, solve for whatever you need to do, and then tell me, was this collision elastic or inelastic? So, let's try it out. Actually, hold on a sec, I need a flag. Through the power of video editing, you didn't hear anything I just messed up on. So let's try it again. All right, ready? So, I'm going to hit clear. Okay, and I'll hit stop there. So what you should have noticed was it had momentum only in this object in the beginning, and then once they collided, then this object moved, and this object was essentially at rest. So that's the information you have. The velocity through the first object, at least I'll give you the time, then you just take this diameter and divide by that time, was 0.0905, 0.0905, and the time through the second, or the time through the second one, in order to get the velocity for the second object, was given by okay, so what you should have sort of noticed was that the mass of this object essentially comes to rest, and then this object takes essentially all the momentum, roughly. The time for this first object was given by 0.0943. If you take the diameter, the length of this, divide by the time here, you'll get the velocity initial. and the final velocity was only in this object right here, and that time is equal to, I'll put it up here when I'm done editing, 2515, what is that, 0.2515. Okay. Really quickly, let me just tell you what the masses for each of these objects are, so that way you can actually do the calculations. For this one, you don't have to do the graph. So just tell me from the data that I just gave you whether it was elastic or inelastic and show it using equations, okay? So mass 1 was 0.86 kilograms, and mass 2 was 1.04 is what I should say. 1.04 kilograms. So 0.86 kilograms. Mass 2 is 1.04 kilograms. And lastly, the mass of this object for the first experiment was given by 0.3 kilograms. So when you're doing the percent error, the actual mass of object 2 for the first part of the experiment was 0.3 kilograms. All right, you have everything that you need. I'm leaving because I'm actually not even supposed to be here right now. I don't know what I'm doing here. So you didn't see this video after you did the lab, okay? Adios.